Hi, I'm recording this video as an introduction to the course Physics 110 at Edmonds College. I'm recording this on September 21st, 2024. And I thought that what I would do is kind of walk through the first chapter of the book to kind of give you a sense of what it's about. So the book that we're using is called Energy, Its Use in the Environment by Hendricks and Wade. It's the 6th edition. And one of the things I wanted to show you about that is about the authors. So if I go to the About the Authors page on the online textbook, I'm going to skip over Roger Hendricks and focus on Rachel Wade, and you will notice that she is a faculty member at Edmonds College in Linwood, Washington. She's in fact the department chair and my boss. Really fantastic teacher and really fantastic physicist. So physics books often get rewritten a number of times. This is the 6th edition of this book. So Dr. Wade was involved in editing a new version of it to update all the details. The physics didn't change, but because the framing device of this book is about energy and its impact on the environment, some of those questions do change over time because the conditions out in the world change. So what I'm going to do is I'm going to walk through the graphs in this first chapter and talk about what they're telling us. There's a story they're telling us about energy and the environment. And you might say, well, what does that have to do with physics? I thought physics was about things like protons and neutrons and neutrinos and fission and fusion and motion and energy and momentum and collisions and things like that. And it is all of those things. All of those things are how we understand the world by breaking it down into its most fundamental pieces. But the implications of all of those play out in a number of different ways, and they can help us understand the real world. And the real world that's really important to us at the moment, and why the class is framed the way it is because there's important considerations for the near future about energy and how it's impacting our world. So let me start looking through some of the chapter. I'm not going to read it. What I'm going to do is I'm going to look at the graphs, because the graphs tell a visual picture of what's going on. You should, of course, read the book. That's one of the assignments. You should read this and think about what it's saying and answer the questions and take notes and use it to inform your understanding of physics and energy. So I'm just scrolling through until I find a graph to look at for the moment. Here we go. Here's our first one. So this is a graph showing on the horizontal axis time. And it starts in 1860 and goes all the way to 2020. And on the vertical axis, we have departures in temperature in degrees Celsius from the 1961 to 1990 average. So if you see a temperature that's on this line that's in the middle at 0, that means that particular year, the average temperature around the world was very close to the average temperature around the world in 1960, between 1960 and 1990. And actually you can kind of see that most of those temperatures in the graph are close to 0 between 1960 and 1990. But you see, before those years, it was a little bit lower, but it fluctuated quite a bit. And then since around the 1970s, it's been steadily increasing with this up and down pattern. And there's a couple things going on there. There's a reason why there's a periodic pattern of going up and down in those average temperatures. But there's also a reason why that average temperature is tending to increase over time. So what we're seeing now in the last few years is that the average temperature around the world is around 1 degree Celsius hotter, warmer, than it was 50 to 60 years ago. 1 degree Celsius doesn't sound like a lot. In fact, it's really not a whole lot for 1 year or 1 day. The temperature in 1 day varies, sometimes 10 or 20 degrees, sometimes 30 degrees in 1 day. So one of the interesting questions is why is it such a big deal that the global temperature is changing by a whole degree Celsius over 50 to 60 years, even though 1 degree Celsius doesn't sound like a lot? And the reason is that in order to change the temperature of the whole globe by that much, it takes an awful lot of energy. And the impacts of that and the way that it impacts the environment and animal life and sea ice and a number of other things have really profound implications for what's going to happen to our planet going forward. So this is a fairly famous graph that you can see in a lot of sources showing temperature change over time. And there's a lot of good evidence that this is correct. Okay, this is a similar graph going back 1,000 years showing carbon dioxide concentration in the atmosphere. So from the year 1000 up to the year 2000. And they measure the carbon dioxide concentration in parts per million. And that means essentially that they took a sample of the atmosphere and counted up all the molecules of different kinds that were in it and said, well, how many of those molecules were carbon dioxide out of a million? So like if we counted a million total, how many of them were carbon dioxide? And you see that for a really long time, that stayed pretty consistent around 280 of those molecules out of a million were carbon dioxide, which is, that's a really small number. 280 out of a million, that's not very much. But starting around the year 1800, that started to steadily increase and has increased up to almost 400, over 400 parts per million in the last 20 years. So one of the things that's going on there is that it seems like there's a correlation, a connection between how much carbon dioxide there is in the atmosphere and those temperatures that we see. Of course, the scales on these graphs are not quite lined up. This one only goes up back to 1860, where this one goes back to the year 1000. And then here's another graph showing the methane concentration in parts per billion. So going back to the year 1000, it was 750 parts out of every billion. So that's an even smaller number, actually, of methane. But that also started to increase steadily starting around the year 1800 until it's up to nearly 2,000 parts per billion in the last 5 years. Methane turns out to be an even stronger impactor on how much heat our planet is able to contain. So here's another, it's a table in the book, Our Earth Then and Now. So it's showing the population of the planet going back the last 50 years. So in 1970, the population was 3.3 billion. For reference, I was born in 1976. I'm 48 years old right now. So this was a little bit before I was born. Then in the year 1990, it was up to 5.4 billion. Then in the year 2010, it was up to 6.8 billion. And in the year 2020, it was around 7.8 billion. It's more than doubled in the last 50 years. We have more than twice as many people on the planet as we did 50 years ago. That's a huge growth. And that actually sounds weird because like I'm used to at this point throwing around the number 7 to 8 billion for the number of people, but it actually hasn't been 7 to 8 billion for that long. It was only 3 to 4 billion when I was born. This next part is showing lead in 10 to the third 10 tons of lead. So what that means is these numbers are thousands. So that's 204,000 tons of lead were emitted in the United States in 1970. And this one's cool actually. It's decreasing. We figured out ways to pollute less in terms of lead over the last 50 years. Then it was only 5,000 tons of lead in 1990. 1,000 tons of lead in 2010, and less, and well, it's hovering around a little bit more than 1,000 tons of lead in the United States in 2020. So we steadily decreased, and now we're kind of like holding steady low, even though our population is continuing to grow. And then you see in the next row, waste recycled annually, 8 million tons in 1970, 49 million, 83 million, 69 million. So we were increasing the amount of waste recycled, and then we've decreased in the last 10 years. There's a number of things going into that, but one of them is that In the US, it's actually really difficult to find places that will recycle all of your waste, often because it's actually so messed up with stuff and not clean enough for them to be able to recycle effectively. And in the next row, you see garbage generated annually, 120 million tons in 1970, 160 million tons, 250 million tons, 290 million tons. So that one's been increasing over the last 50 years. So maybe slowing down a little bit, but it's still increasing. This one's really interesting and cool. The percentage of oil imported to the United States. In 1970, 23% of the oil that was used in the United States was imported from other countries. And then 51% of the oil was imported to the United States in 1990, 53% in 2010. Is that right? Yeah, 2010. And then, so we were seeing an increase in the amount of oil and the percentage of oil that we were using that was coming from other countries for a long time. And then it dropped dramatically in the last 10 years. So that negative 5% means that we're actually exporting oil on net to other countries now. And that's because of both discovery of new oil resources in the United States that allowed the U.S. to be able to be an exporter instead of an importer, and also repurposing other energy sources so that we didn't need to be burning the oil ourselves and we could sell it to other countries. But that also has some secondary consequences about pollution and climate change because of how much energy is being used. This next one is about percentage of the United States federal budget that's spent on the environment. 3% of the federal budget was spent on the environment in 1970, 1.5% in 1990, and then 1.2% in 2010, and 1.2% in the last 5 years. So that one's been decreasing. So a lower percentage of the federal budget each year is being spent on the environment. All of that is going along with that graph that I showed you, that the concentration of carbon dioxide in the atmosphere has been increasing steadily over that entire time, from 325 parts per million up to 413 parts per million. And the entire global emissions of carbon dioxide have increased during that whole time, from 14 billion tons per year, the 10 to the 9th corresponds to billions, to 23 billion, to 33 billion, to 35 billion tons of carbon dioxide emitted every year. Huge. I'm going to pause for a second right there. So I paused there for a second and I skipped ahead so that I can try and keep this from getting too long. It's easy for me to just keep talking and talking and talking. Now I'm looking at a graph a little farther along in the chapter that's looking at energy consumption in the United States between 1776 and 2020. So since the founding of the United States up till almost today. This one's measured in quadrillion British thermal units, which is a really weird unit. British thermal units is one that's traditionally used for measuring heating oil. And quadrillion is a really large number. So you can see, like, it's tiny. Everything's tiny down in 1776 because the population of the United States was tiny compared to today. It was not anywhere near the 300 plus million people that we have today. So you can't even really see a separation between the different kinds of fuel until around 1900, where you can see that the majority of it is fossil fuels, coal, natural gas, petroleum, and very little of it is anything else. And then in 1950, it's still majority of petroleum, natural gas, and coal. And then, like, frankly, this graph is showing that it hasn't really changed very much. That the total amount of energy that we're using in the United States is growing a lot and growing faster than the population is, which means that people are using more energy per person than we used to. And that makes sense if you think about all the electric lights and the air conditioning and the cars and the computers and all the things we do, that just adds up. So that everybody's using more than people used to. and there are more people than there used to be. So the total energy consumption is growing quite a bit. And it's still, the majority of it is still petroleum, natural gas, and coal. And then 21% of it is things that aren't fossil fuels. So that means almost 80% comes from burning stuff. And burning stuff is always going to lead to putting more carbon dioxide in the atmosphere, and that's going to lead to the climate change issues. And of those that are not burning stuff, it includes nuclear energy, which is one of the things we'll talk about in this class quite a bit, and wind, and biofuels, and hydroelectric, and all other renewables. So renewables are things that essentially grow on their own or are produced on their own in a way where we won't be using them up because we keep getting more of them. An interesting thing in Washington State where we live is that hydroelectric is actually higher in Washington State than it is in most other places because we have the long-term investment of the big hydroelectric dams that were built in Washington State and in Canada and along the Columbia River almost a century ago now. And those dams are still producing energy and will still produce energy for a long time. And that actually makes electricity prices in Washington State considerably lower than they are in most of the United States, and considerably lower in climate impact than they are in most of the United States. But if we're thinking about energy policy for the whole country, we have to think about where those sources are coming from for most people, even though it's a little bit different for Washington State. So then I wanted to look at, I'm going to skip over some graphs here. Actually, I wanted to show this one showing world energy consumption per country. And the last time I made a video like this, this was actually flipped. So currently, China is the highest total energy consumption in the United States is second, and India is third. And only about 5-6 years ago, it was the other way around. The United States was higher than China. And it's really not surprising that China should have a higher total energy consumption because China has a much larger population than the United States. But it also already had a much larger population in the United States. And the reason that its total energy consumption was lower was because the amount of energy use per person was also lower. And one of the things that is saying is that the standard of living, of what people are able to do, has increased dramatically in the last 2 decades. And that has largely come from the ability to harness more energy sources. And then I wanted to show one other graph in this section, which is the different uses that energy is being put to in the United States. So 33% of the energy that's used in the United States is used in industrial sources, in industrial uses, making things. 28% in transportation, moving things around. 21% in residential, in our houses. This is the stuff that is directly attributable to what people are doing. And then 18% in commercial, in places of business, and where you're working, but not in the actual making of things. So that says like the largest part of our energy use isn't coming from personal choices. Almost 80% of it is coming from business uses. But still a large portion of it is from personal choices, and some of those personal choices are coming from transportation in terms of like how much stuff we have shipped to ourselves and how much stuff needs to be moved around in order to be able to support our standard of living. So I'm actually going to stop there in walking through the chapter because I don't want this video to get super long. It's already a little bit long. One of the things I want you to do is I want you to be reading the book, and I want you to be looking in particular at these graphs because they tell a story that help you understand what's going on with energy. And as we get deeper into the quarter, we're going to learn about how to use the tools of physics to understand where energy comes from, how it gets used, and how to think about the impacts of choices that you make and the choices that the entire economy makes impact the rest of the world. And I think that the mindset of how we use physics to think about things will help us to understand that better so that you can make better choices and so that you can help influence people to make better choices, however you decide those might be. So thank you for listening to this long-winded introduction. And then I encourage you to read the rest of that first chapter, and then I'll be making a few more videos about some of the physics work that we're going to do connected to energy.